right, so let me just read this to you here. The troposphere is closest to Earth because the density of air decreases with altitude because there's less air pushing down. The troposphere's temperature will decrease with altitude. So the pressure, stay with me here, pressure affects the temperature. So let me read that again. Because the density of air decreases with altitude, as you move up the troposphere, the pressure decreases. There's less air pushing down, so therefore the temperature decreases. Temperature increases with altitude in the stratosphere. You should write this down. So temperature increases with altitude in the stratosphere because the sun's UVB and UVC warm the upper layer. I believe, I might have wrote this down, I don't think I'm making this up. I believe the UV rays interact with the air particles in the stratosphere and turn it into infrared, which is why it heats up. Let me see if I wrote that down, or if I'm making that up. No, it is what happens. The upper atmosphere absorbs a lot of UV and converts to infrared, which is released as heat. So in the stratosphere, due to all that UV, UVB, UVC, it interacts with the particles and changes to infrared, or creates infrared waves, which basically is heat. Things that are warm give off infrared radiation. So that, I would write that down. In the stratosphere, you have UVB, UVC. If you just remember ultraviolet, that's fine. But it's converted to infrared, and that's where the heat comes from. That's why the temperature increases with altitude. That's a great thing for us. What?
Ice Age?
No, think about, we're below that, right? So you got all these infrared, UV hitting, turning to infrared, getting hot.
So UV rays aren't coming?
Right, UV rays, we're not getting hit with even more. We're getting a whole bunch, but there could be even way more than that. But the ozone and stratosphere are blocking a lot of it heating up. So that's a good thing for us. I don't have anything on UVA. I'm pretty sure there's A, UVA. So I don't know what happened. Maybe that just goes straight through. Maybe that's more of a problem. I don't have anything on that. All right. Now, so I have something here on the thermosphere. The thermosphere blocks X-rays and UV. Why don't you write that down? So, look how thick the thermosphere is compared to the little tiny ones down here. It's ridiculous. It goes from about 85 kilometers to 600. So the thermosphere is extremely...
What does it block? UV?
Blocks UV and X-rays. The thermosphere also contains those ions I was talking about. So write that down. So thermosphere blocks X-rays and UV rays. It also contains ions. So when sunlight hits the thermosphere, especially at certain altitudes, usually near the poles, because there's a more concentrated amount of ions due to magnetic fields. And when the sun sends light towards us, it's full of other radiation and other charged particles, tons of charged particles. So when it hits the thermosphere, it can interact and create the northern lights, aurora borealis, or southern lights, which is aurora australis. Yeah. I would like to see that someday.
What?
Like in person.
I want to see
Sometimes they come down as far as like the Dakotas. So it's pretty cool.
Leave the States.
Right. I have no problem going to Canada, but yeah. So anyways, that's what I have on the atmosphere. Moving on, but this is cool. Look at this. Temperatures in the thermosphere can reach 1,750 Celsius. That's about 3,000 Fahrenheit. It's crazy.
Is
So-
there no temperature in the exosphere? Is that just like not a thing?
That's pretty much like space. There is temperatures, and depending on where you are in space, it can be very hot or it can be very cold. The problem is the particles are so spread out that
It doesn't really transfer.
right, it doesn't transfer. It's kind of like my thing when I talk about if you put your hand in boiling water, it will hurt really bad. But if you put your hand in a 400-degree oven, you can keep it in there for a few seconds and it won't even hurt. It'll just start to get warm. And that's because the oven, the air, not touching the racks. the air is very spread out, so it doesn't transfer to your hand as well. So it's the same thing here. So temperature, I would argue, I could be wrong, but these high temperatures in the stratosphere might affect us more than these high temperatures in the thermosphere because of the expansion of the particles. But I don't know. We'd have to test it.
What do you mean?
Like transfer to it, like we feel it more down here than up here, even though it's hot.
The troposphere, the heat of the stratosphere is about the same as us, so that won't really affect us.
Right, but the point I guess I'm making is I think our body would feel it more here, even though this is way hotter. We probably would because it's so expanded. But I kind of like the water with the versus the oven. All right, moving on. Okay, the amount of solar energy reaching Earth varies with location. So let's kind of paraphrase some of this and just get bullet points. So it says that the sun's energy passes through the atmosphere, strikes land and water, it warms the surface, but warming does not occur evenly. So just as long as you know that, you don't have to write it. If you need to write it, go ahead. But warming does not occur evenly. That affects the weather, the air currents, wind, the ocean currents. So stuff we're going to hopefully learn all that right now. The angle at which the sun's rays strike varies. We just demonstrated that with the flashlight. So yeah, actually, why don't you get these bullets? These are good bullets to put down. The surface area is the key, and I didn't really teach that very well back there. But when the light was shining on, let's say, South America very brightly, that is very intense, meaning a little tiny area has a lot of sunlight. Well, if you were to look at the globe, it was darker near the northern hemisphere because the light was expanding or stretched out, not expanding. The angle was very flat angle, so or oblique as Will used earlier. So it's not as concentrated. So the sunlight is distributed over a longer area. So another way to kind of think of it is if you have the same amount of sunlight here versus here, right? So if you have a certain amount of sunlight coming from sun hitting this little area here, you take that exact same amount and you bend it so you're stretching that light out at a different angle. So the same amount of light spread over a larger surface area, it's going to be cooler. That's like holding a flashlight flat against the table or holding it at an angle. And that's what I was trying to show you with the globe. I think you guys, I hope, get that. So that's what they mean by surface area. So at the equator, there's always more intense, meaning more sunlight in a smaller area. And at the poles, there's less sunlight in a larger area. Does that make sense to you guys? And the albedo, some areas greater than others. And water has a different albedo than forests, right? So we talked from the very beginning of school about the fluctuations in that CO2 graph because of the season changes. And northern hemisphere has more or less land than the southern hemisphere. More. So because of that, and the land absorbing energy differently than the water does, that affects unevenly heating, right? So the percentage of incoming sunlight reflected from the surface. Why don't you write this down? Earth's average is 30%. So 30% of the sunlight that comes in is reflected out. We're doing a real good job at trapping it, though.
Are you talking about solar panels?
No. Talking about the blanket we're putting around the Earth. Greenhouse gases.
Well, solar panels.
But you're right. Solar panels take it and convert it. You're right, though. He's not wrong. That's just not where I was going. All right, so I'm just going to kind of paraphrase some of this that I have written down here. So there's three things that affect why the Earth is not heated evenly. The angle at which the sun strikes the Earth. I think we just talked about that. We're good. The amount of surface area that it is distributed. That's kind of one and the same there. So the equator is the most direct throughout the entire season, all year I should say. One thing I did want to mention about this though is, and this is why sunrise and sunset the sun and the atmosphere changes color?
What?
Doesn't really change. I mean, I don't want to get into this argument about colors don't exist and
What are you
stuff.
talking
But, you know, so like if you're outside at high noon, what color is the sun?
Yellow.
Whitish, yellow, right? And the
Nothing
sky?
to do with the sun, so I don't know.
Right, okay, don't look at the sun.
Everyone follows the rules.
And what about the sky? Blue. Okay, what about sunrise or sunset? Red, pink,
It's
purple,
cool.
orange. Right? Different colors, reddish, oranges, right? We agree? In general?
Does that
Okay.
mean the ocean changes colors?
Yeah. Anyone who really means that, I just want to shake them until they listen. Now, I don't know where that came from. It's like,
What?
it's
What?
like people will believe anything.
What?
What
Matter.
came from?
What
Blue
came
because
from?
of the ocean.
That the sky is blue because the ocean's blue.
Wait, I believe that. I
It's
believe
just so
that for a
crazy
long time.
because if you take a glass of water, it's not blue. All right. Anyways, so, yes.
We have a
Wait,
small
why
question.
is it
actually?
why
Why
is
is
it
it?
All right, I'm about to explain that, and there's a cool, you know what? Remind me the next couple days. All I have to do is I have a big tank in the back. This is why I don't get through everything. I put the tank on the lab table. I fill it halfway with water, and I put a couple drops of milk in it, and it gets like a little. I know it sounds gross. I know.
Foggy.
Foggy, right?
Milky water.
This is a cool demonstration. Take one of those superpower flashlights. I have a really good one at home, and you hold it on the side of the tank, and we all stand on the side of the tank and look at it. And then we all go to the end of the tank and look at it. And then I do the same thing with the flashlight on top.
And then we look at it from the bottom.
So, well, you look at it at different angles, and the point is, I'm about to make this connection here. It's a cool demonstration. In fact, Mrs. Snyder watched it a couple years ago. I did it with astronomy, and she was like, "I never knew why." It was like pretty cool. It was like a moment for her as a student, but she was a teacher. It was kind of cool. Anyways, it's the best demonstration for this. So, why is the sky blue during the day, and then evening and morning when it's rising and setting, it's more gold or pinks or whatever. So, there's two things. So there's two things. For some reason, and I don't have a great reason, the air particles and what our atmosphere is made of does a much better job scattering blue light than any other light.
Yeah.
So that's why it's blue. But it has to do with the angle of the sun. When the sun's angle is very direct, it will be blue all the time. Every time it will be blue because it scatters blue light very well when it's direct.
Are you saying that the poles, the sky's not blue?
Let me finish. So, before we keep going down different rabbit holes, just stay with me. So, when the sun's directly overhead, which it's not here, it'll be blue because think of you have an atmosphere. When the sun's rays are fairly direct, the atmosphere does a great job. Hello. Oh, okay. I got a class till 11. He's an hour early. Okay. Yeah. Well, yeah, but I can't. I got stuff going on next period too. Because it's not till 6th period. Okay. Thanks. Bye. All right. So when the sun's rays are direct, the atmosphere does a great job scattering blue light out of all the colors that it could scatter. So that's the Roy G. Biv. However, when you take the sun, so you have your atmosphere, think of the globe, and you bring the sun at a different angle, the sun's light, and this is not a good way to show it, but that's what the demonstration's for. The sun's light has to travel through a much larger area of the atmosphere. So if you can just imagine a strip of air in front of your face and you're holding a flashlight above it, The light can go straight through that thickness. Well, if you bring that flashlight to the side, now that light's traveling through all of the atmosphere. So when sunlight travels through all of the atmosphere and it's not cutting through it, it scatters the reds and the oranges and the pinks better than the blue. That's why the color of the atmosphere changes. It's because it has to cut through more atmosphere, which scatters different types of light better than blue light, which is more of a direct, straight through the atmosphere. That's why the sky changes color. That's why the sky is blue most of the time. I mean, it's gray right now. So that's why. It's nothing to do with water, the ocean, this crazy stuff. It has to do with light and how it travels through the atmosphere. So, what does that have to do with what we're talking about? It also affects the heating. So it's going to be more efficiently heated here, less efficiently here because of that angle. So that's kind of two things at once going on there. So isn't that interesting?
Yeah.
Yeah, I think it's interesting. Now you know. Remember that and teach the world. It's not because the ocean's blue, because the ocean
We're gonna
isn't
make
blue.
a difference.
What's that?
We're gonna make a difference.
We are going to make a difference. And the reason the ocean is blue in different colors, and you asked me this early in the year, it has to do with the compounds and what's in the water at different parts of the world. So there's
The clear.
the clear versus like the Caribbean blue, you know, like looks like this, or like some are like gray. It has to do with what's in the water and how the light's being reflected and scattered. It's more of the same. All right. Okay. So there's that. Albedo, we're moving on. All right. So as far as the seasons here, write what you want to write, but you do need to know the difference of everything we talked about on the whiteboard. So we're tilted 23.5 when we are tilted towards the sun, and the southern is tilted away. That's when we have our summer and they have their winter. So that all you need to write is 23.5 degrees is the tilt. And then this image, it's kind of hard for you to see here, but it kind of covers everything here. So it shows the June solstice. Summer solstice is over here where the Tropic of Cancer, that's 23.5 north, is going to be directly overhead. The December solstice, winter solstice, the Tropic of Capricorn, that's where the summer, or southern is facing the sun. The equinoxes, again, it's like the earth is on the side of the sun. Now, it sounds crazy, but that's how I think of it. So look at this picture here, it's all illuminated equally because that's the equinox. So at the spring and the fall, the tilt doesn't really factor in. I wrote down some notes here, some things that you can get down. So spring equinox is March 20th or 21st, and the fall is September 22nd or 23rd. And it says here, in September equinox, sun is directly overhead at the equator, and all regions of Earth receive 12 hours of daylight and 12 hours of darkness. So that's why it's equinox, because you have 12 hours of daylight, 12 hours of darkness on the equinox, and it doesn't matter where you are. Kind of cool. 12 hours isn't very much. You know, it's funny, not funny, but my father-in-law is from Peru, I've told you that before, which is very close to the equator. So his day and night has been most of his life until, well, he lived here most of his life at this point. But when he was a kid living there, it was like light and dark, fairly equal amounts. And then he said, yeah, you know, it was weird here getting used to all the daylight or all the darkness depending on the season because he lives so close to the equator. So it's just interesting talking to him because I have no concept of that, except here. So the equinox for us is more like the equator kind of all the time because it's fairly balanced throughout the year. December solstice, you're going to have less sunlight at the northern hemisphere, more at the southern. Shortest day for us, longest day for southern hemisphere. Summer, longest day for the north, shortest day for the south. I'm just kind of repeating myself here. I'm trusting you to write down what you think you need to write down. Again, March 20, maybe you want to write these down. March 21st or March 20th is the spring equinox or vernal equinox. The fall or autumnal equinox, September 22nd or September 23rd. Let's see here. What's that?
I just put equinox.
Oh, EQUINOS. EQU.
What was the other word for the fall equinox you said?
It's fall or autumnal
Yeah, how
equinox.
do you spell that?
Autumn, except it's AUTUMAL.
What's the date for the fall?
Fall is September 22nd or 23rd. Spring is March 20th or 21st. Yeah, you know what? Back there when I was talking about the 6 months of light and dark at the poles, yeah, I knew I was right and wrong at the same time. I kept using the wrong dates. So it's easier when you see it here, because it's hard to kind of sometimes for me to think about it. So from, where's the spring? Spring. So from the spring equinox to the fall equinox, yeah, that's 6 months, right? Yeah. So you're gonna have more sunlight in the northern hemisphere and less in the southern for that 6 months. So from your spring here to the fall, you're gonna have the most sunlight on the northern hemisphere, less on the southern, and the opposite. So from the fall to the spring, which makes sense, right? And that's our seasons. You go from spring to summer, right? So anyways, going this direction here, more sunlight on the north, not on the southern. And then the opposite is true when we go from the fall to the winter, back to the spring. You're going to have the most sunlight on the southern hemisphere, at least on the northern hemisphere. And you can kind of see it with the shading here. So as soon as you start getting away from the spring, you see the light on the North Pole stays constant the whole time, then it starts to go away here. So, and then the opposite for the southern. Let's see, June 20th, June 21st, that's your summer solstice, June 20th, June 21st. Most sunlight of any day for the northern hemisphere. And then the winter solstice is December 21st or 22nd. In astronomy, we talk about that a little bit. You go back to the Scandinavian countries. Apparently, this is what history or legend says, they started celebrating the winter solstice, and then that got morphed into Christmas as Christian religion got mixed in with the Viking religions, and it's kind of like what came first, right? I'm not one to decide that, but both kind of celebrations are around the same time. So some people think the winter solstice and Christmas and all the holiday celebrations of a lot of religions are around the same time because of the winter solstice. Because way back when, people didn't really have time. They used the sun and seasons to kind of celebrate different things. And that was a big deal, the summer and the winter. So it's kind of interesting. So December 21st, December 22nd. All right, you feel good about seasons? You know what's happening here? Okay, good. All right, air currents. Here we go. Let's get all these words down, and then we'll talk about them. How much time do I have? Not enough, but we'll do what we can. So just get these definitions down, and then we'll talk about them. So you got saturation point, antibiotic cooling, antibiotic heating, latent heat release.
Is that the same thing as dew point?
No.
Saturation point? The water vapor in the air?
I mean, it's similar. Dew point has to do with temperature.
Doesn't that
And
say
it
at a
also,
given temperature?
it does. It also has to do, alright, maybe I answered too quickly, but I don't think it's the exact same. I can't remember dew point off the top of my head, but I know there's a calculation involved with that, but there's probably one with this too. So let me take back my answer and I'll have to look into it.
Because you were like immediately no.
Well, because they would call it the same thing if it was the same thing.
There's different names for.
You're right. I don't know, I have to look into it. If it isn't the exact same thing, you're right, it's very similar, so it has to do with the amount of water. But humidity does too. The antibiotic cooling or adiabatic cooling, these words I struggle with. These cooling and heating effects are like the reason life exists, essentially. Because air heats and cools up and rises and sinks and it affects the ocean. Oceans do the same thing, but it's all connected. It's kind of crazy once you learn about all of it, how everything is connected and it's all necessary. And it's really scary how we're altering the temperature of the air in the ocean, and that's affecting all of what we're going to learn. It's just scary. I keep forgetting to tell you guys about leach fields. You guys all have septics, right?
What?
Septic tanks, septic systems, you have to. Because you don't have a sewer system. Leach fields, kind of gross. Anyone know what a leach field is?
Yeah,
Where it
beavers
drains off.
Where what drains off?
Excess
Bathroom
Liquid
stuff.
waste. Yes.
poop water.
Liquid waste. The solids shouldn't make it. Maybe small particles. But what kind of soil would you want for your leach field?
Sandy.
Yeah, sandy. You don't want clay. Why?
It'll fly over the
Especially if it rains, it'll just come up to the surface. And you want it sloped downward as well,
Isn't
away
that
from
when
your house.
the grass grows really well there?
Yes, it does. So it's just, I talked to Mr. McCauley about it, and you know, some people, depending on where they want to live, you know, they might have to dig out a pretty big area for that. If there's a lot of clay, let's say, you have to take it out and fill it with sand or more sandy type soil, so they can have a successful leach field. Because you do not want that backing up.
Just recently I've had beavers in my house, and the dam saturated our leach field, so water.
So they recently put a dam somewhere, and that
Yeah.
caused water to be diverted towards your house.
Yeah.
That stinks.
We just got it. The beavers are gone now. As a couple weeks ago, the trapper said this guy who's been doing it for 20, 30 years said it was the biggest beaver he's ever caught.
All right.
It was 70 pounds.
70-pound
Yeah.
beaver. Whoa.
You gotta make a hat out of it.
That's a serious beaver.
Yeah.
They're keystone species, man. Don't kill them.
Yeah, until it's killing the houses.
Listen, I get it. I get it. We all have to live together.
Killed my property.
All right, are we ready to move on here?
Yeah, seriously. Wait, I need the last one. It's still theirs.
I know, but I didn't know.
You have 4 minutes.
Okay.
I can get it in 4 minutes.
I want to give you another word here. Water vapor capacity. So we'll just get all the terms out of the way, and then we can start explaining, and obviously I'll pick up tomorrow. Water vapor capacity. What does it sound like?
The max amount of water vapors.
Flux capacitor, fluxing. Yeah, it's the amount of water the air can hold, which is kind of like saturation point, but that's at a given temperature. Water vapor capacity is just basically the amount of water at any given point that the air can hold. What you need to know about water vapor capacity is that warm air holds more or less water vapor than cold air. More. Warm warm air holds more water vapor than cold. There's lots of reasons why it doesn't rain at the North Pole, but one reason is it's a lot drier. Where is it really wet and warm and it rains all the time?
It's really cold there.
I know. Forget that. Forget the temperature for a minute. Where's it rain the most? Rainforest, where it's hot and humid, right? So, but that's because of the water vapor
Well,
capacity.
like the Sahara is kind of near the equator.
Right. So the Sahara is different because there isn't a lot of moisture. So we'll talk about that. All right. So let me just kind of start talking about something here. All right. So you guys read a little bit about this, didn't you?
Now,
Air currents.
oh
Yeah.
What essentially causes air currents?
Different
The
temperature and
cooling
pressure.
and heating.
Different temperatures, heating. Okay. So what happens to hot air?
Rises.
Rises. What happens when it rises?
The other stuff has to replace it.
no, it condenses
Yeah,
and
please.
it gets colder.
So it starts to cool down.
It's like a
What
big
does
old
it do
circle.
with its heat?
Release.
Transfer.
It releases it. What term is that? There's two terms. As warm air rises, it starts to cool, so it undergoes
Adiabatic cooling.
adiabatic cooling, and
He doesn't know.
it releases energy when water vapor in the atmosphere condenses. So this can happen as well. So we have warm air with water vapor. As it rises, it experiences cooling because of the pressure change, and then it releases or condenses that water vapor. What's going to happen? You have a whole bunch of water vapor that's condensed and gets cooler.
So it rains.
It rains. Now, that cooler, dry air does what? Where's it go? If warm air rises,
Cool air drops.
cool, dry air drops. And what does that create?
A
A
circle.
convection current. A
Hadley
circle.
cell.
Right, a convection of the cells, right. Hadley cell is one of them, Fresnel cell. So we'll talk more about that tomorrow.
It's a circle.